Lander Challenge. I'm Noteboom, and I want to let you know we have Alan Newcomb here, who's our team leader today, as well as Bonta, another team member. And we're going to tell you a little bit about the team, a little bit about our vehicle, and hopefully show you some videos that I think you will enjoy. So first, let me just start with the mission of our team. Well, it's very simple. We wanted to build the smallest, lightest, simplest, and best lunar lander because we thought that's what it would take in order to win the Lunar Lander Challenge. And so we put together a team with a small team of experienced people that we thought had the right experience and brought the right skills to our team to build this vehicle. And I've got a picture over here. I'm going to tell you a little more about each one of them. We've got a group picture. Unfortunately, I wasn't there that day, so that's me there up in the upper right. And we even have a mascot, so that's Scott. Okay, I mentioned Alan Newcomb. He's our team leader. And he's got over 20 years of experience in developing avionics, not just for aerospace vehicles, but also for racing and other extreme environments like down oil wells. He designed, I guess more recently designed all the avionics and flight software and ground software for the space dev effort on the hybrid rocket engine for Spaceship One. And also for space dev, he put together the electronics and some of the mission control software for the chipset. Okay, I'm the second member of the team. I'm an aerospace engineer, at least by training, and earlier in my career I worked at NASA, Space Shuttle Guidance, Navigation, and Control. So the type of thing I'm doing on this project. Way back, I was a founding member of Microsat Launch Systems, or International Microspace. You may have heard of that company. Back in the late 80s, early 90s, we were working on developing a small vehicle to launch small satellites on the order of 100 pounds into low Earth orbit. And I was the program manager and lead designer for that vehicle. And since then, I have sort of returned to working with NASA and led a number of programs, most having to do with software development, usually flight software development or verification. Dan Kent's the third member of our team, and he's working on the airframe and the structure production. And I guess the best way to describe Dan is he likes to build things. You know, starting with building a company. He was the founder of the computer engineering group, a small company that did software and hardware development. But he recently sold that and brought his skills not only in project management and building things to the project, but also his experience as a pilot. If you're trying to fly something, it's good to have at least one person who's really a pilot on the team. Dario Donovan is our engineer machinist, and basically what he brings is experience from the auto racing industry. He's been engineering, designing, building race cars for the past 30 years. He worked on top alcohol dragsters and Formula One Mazda racing. He won several national championships. Also, he's got a fully equipped machine shop, which you'll get to see a shot of, or at least part of the shot of that in the future. He's normally servicing about 6 race cars in there at any time. And he's the original manufacturer of the Cygnus flight computer. Because I forgot to mention earlier that way back when we were doing that startup with Microsat and International Microspace, that's when Alan Newcomb and I originally met. Alan was the designer of the flight computer. Dario O'Donovan built it. And then we have our creative director, Bonta, who brings her imagination and innovation to the team. She's an acclaimed novelist and award-winning poet. She's the creator of the novel Flight, and was recently featured on the History Channel's The Universe, where she tested one of her inventions, the 2-suit. Some of you may have seen that. She's also a co-inventor of one of the systems that I'm going to talk about later, the
rocket engine overpressurization release system.
Overpressurization release system. So our basic approach for the competition was to do 2 things. First, to build upon the team's past experience, both in aerospace vehicle development and also in auto racing. And I've just sort of listed some of the projects that we've worked on. Alan and I worked on the Microsat systems together. He also worked on Spaceship One and on ChipSat, whereas I worked on the shuttle program. On the auto racing side, actually, both Alan and Dario Donovan have experience there. Dario being a sort of hardware designer and a driver. Alan was also a driver for the Formula Ford race series and worked at data acquisition on dragsters and on an IndyCar team. So the second half of our approach is to leverage the multi-billion-dollar investment made every year in the auto racing industry. And we think of space as being expensive, but $3 billion isn't really chump change. I mean, they spend a lot of money every single year developing technology so that they can race and beat their competitors, similar to what we're trying to do in this competition. So let me talk a little bit about our vehicle. The vehicle is the Lauryad. It's inspired actually by a vehicle that is named, that is described in the book that the novel that Ivana wrote, the Flight, a quantum fiction novel. And so the goal of our team was to bring this fictional vehicle into reality. Overview, I guess it shouldn't be a surprise that for the lunar lander challenge that we've got a single stage vehicle, vertical takeoff and landing. That's almost a requirement for the project. It's a bi-propellant engine. The fuel is propane and the oxidizer is nitrous. We use helium as a pressurant. And we use thrust vector control in order to control pitch and roll with rotation around the yaw axis, which is the vertical axis here, being done with an RCS system. Looking down, you can see we've got two tanks to the left and right of center, which are for the oxidizer. The center tank is for the fuel, the propane, and we have room for two additional oxidizer tanks, which are required for the level 2 challenge. Dry weight, our goal was 97 pounds. I actually believe we're a little bit below that now. I think the latest number is actually 77 dry without the payload. Gross lift-off weight is 267 pounds, and our engine is capable of 351 pounds of thrust. So it's a fairly good thrust ratio with being able to throttle down to about 25%. We went for a lightweight structure, so we've got an airframe that is built out of carbon composite, and the tanks are also carbon composite with epoxy. Of course, you need a controller. We've got two controllers on board. A main controller, which sort of senses the environment, reads commands, and drives the thrust vector control and lets you control the vehicle. We also have an abort controller, which main purpose in life is to sit there and initially open up all the fuel and oxidizer valves, and if it decides an abort is required, if it gets abort commanded, or if it loses a signal, it shuts everything down for safety purposes. So let me tell you a little bit more about the airframe and sort of some of the philosophies that we put into building this. The first being that metal is so yesterday. We were trying to go for the lightest weight thing we can do. So we built the structure totally out of composite. I'm not sure if you can really see it in that picture, but you can see the base structure. It's a pyramid with long legs and a platform in the middle, which is where the tanks get fastened to, and all the plumbing and avionics and other subsystems would be attached there. Total weight of that airframe is only 17 pounds, and we tested it under load. You see Ivana there initially, but we actually put over 300 pounds on this by piling up concrete bags.